Swayam Prabha. Digital India. Educated India.
Last time we have been summarizing whatever we covered in this course that far, and we shall continue with that summary. If I recall right, we were summarizing up to concentrating collectors. In this process, particularly on the topic of concentrating collectors, we have defined concentration ratio and the need for concentration, and then we obtained an expressions for maximum possible concentration ratio and the angles of incidence for different modes of tracking, and the RB, that is the tilt factor instantaneous to estimate the solar radiation direct on the concentrating aperture optical efficiency, and then we have expressed the daily radiation received by the concentrating collector's aperture area. Then we have considered subsequently the compound parabolic collector. This is originally proposed by Professor Winston. It is also called as Winston collector, and the focus of the parabola 1 is at parabola 2's intersection point and vice versa, as you can see over here. So, whatever is the solar radiation enters in the aperture AD will be having multiple reflections reaching one of the focal points, thereby transmitting heat to the tube with a fin and tube arrangement between B and C. B is the focal point of parabola 1 and C is the focal point of parabola 2, and concentration ratio is 1 upon sin theta A, where theta A is the half acceptance angle. In other words, the solar rays beyond the angle of incidence between theta A and beyond that, they will not, they enter, but they reflect backwards, they do not reach the absorbing surface. And then we briefly considered to solve some problems, state, city, latitude, longitude are available at the website given. Similarly, sufficient solar radiation data for the Indian locations is available at the other website, which is shown over here. And then we distinguished between a system and a component. Solar collector is only a component in the system, and the system consists of several other components like storage tank, pump, controls, heat exchangers and pipes, and the associated losses or the heat exchanger penalties, which makes the performance of the system different as compared to the just the performance of the solar collector so far, which we have been doing. So, this is indicated unlike by a conventional efficiency for a conventional energy system, we indicate by solar load fraction F. It is the fraction of the load on the solar energy system that is met by the solar energy. If a particular space heating application is considered, for example, on a house, and if it has got 192 gigajoules of yearly load, out of which 180 or 150 gigajoules are met by the solar system, the solar load fraction will be approximately 0.8 or 0.7. So, the cycle of period has been chosen to be 1 year, because the meteorological cycle repeats itself, and also 1 year is a good period for economic analysis. Now, the whole objective of this course had been finally to determine this solar annual load fraction, and first possibility is system scale experiments. Here is where we recognize the difference between the conventional energy systems or for that matter any component and the solar energy. A conventional energy system, but for minor differences, is likely to perform similarly given the same input wherever it is located, whereas the solar energy system utilizability of the energy supplied by the solar energy system will be different depending upon the location. If you are having a space heating application in a cold location like Srinagar, Kashmir, and you want to use it for in Chennai, probably there may be no space heating requirement at all. And system scale experiments are expensive, time taking, and as you recall, if you plot the solar load fraction versus area of the curve over a period of 1 year, if you start with let us say an area of 50 square meters with a certain orientation, then you will get 1 point. Now, another point, another year, another point like that, and possibly you may do with 5-6 points and obtain the curve, this may be 1. Now, the whole point is optimization of the system parameters will take prohibitively long time if somebody wants to change the slope, flow rate, storage capacity, heat exchanger effectiveness, then again this has to be performed. So, if you want to get it in a minimum time period, you may have to get several systems of different areas operating simultaneously along with different orientations, different slopes, heat exchanger sizes. It is expensive. Nevertheless, the system scale experiments are necessary to, for example, validate other possibly theoretical or simulations. Okay. Then also practical difficulties and deviations from our assumptions and approximations. So, TRANSIS is one such modular similar simulation program which has been developed at the University of Wisconsin, and it has got several components like a flat plate collector, concentrating collector, different modes of tracking, Trombe-Wall, passive systems, etc., radiation processor, metallurgical processor, and several other components. So, one can link up the required components and obtain the solar energy performance over a system and change the flow rate or any of the other parameters associated with the system and obtain the performance of relatively very short time compared to system scale experiments. So, this is, however, this also has got certain limitations, requires large database, computational power, and perhaps the skill of experts set up the models for the components. And while this is certainly justified and while this is certainly practically meaningful compared to system scale experiment for large systems, If you have a domestic hot water system DHW, maybe in the Indian context supplying about 60 liters per day at let us say 60 degrees C, this may require approximately 1.5 to 2 meter square of collector area with a standard storage tank of 70 liters capacity or 75 liters capacity, and this may be about 20,000 rupees. Now, simulations almost cost the same thing whether it is a large system or a small system. So, at times even the simulation cost may not be, may be too much for a small system. Further, the need of the industry is to have a quickly calculable, implementable relation to obtain the sizing of the solar energy system needed, which will reasonably take into account the location dependence and for standard systems at least. So, the F chart method and the phi bar F chart method, once again developed at the University of Wisconsin, have been popularly called as simplified design methods. This F chart method is applicable for T minimum. So, if the supply of energy is above 20 degrees C, you can apply the F chart method, and the correlation has been developed for certain ranges of the parameters which have been listed over here, 0.6 to 0.9 for tau alpha normal, similarly area, overall loss coefficient, slope, and the building loss coefficient, which we have explained in the detailed lectures. So, this F has been correlated as a function of two non-dimensional parameters, one the non-dimensional collector loss and the non-dimensional absorbed energy. Both on a monthly basis. So, X is defined over here as FRUL into 100 minus TA bar into the number of seconds in the month into the area upon the load. If UL is in watts per meter square degree C, L will be in joules. So, similarly, Y is FR monthly average transmittance absorptance product tau alpha bar and the monthly average daily radiation on the tilted collector surface multiplied by the number of days in the month and the area of the collector, and if HD bar is in joules per meter square day, L also will be in joules. Of course, you know the other meanings, and so these are all explained for your convenience once again here, repetition. And calculation of load, space heating load is in terms of the building loss coefficient multiplied by the degree days multiplied by 24 into 3600. Basically, degree days means the deficiency or the actual ambient temperature being lower than the comfort condition like 20 degrees C or so. The deficit is indicated by degree day irrespective of the method of evaluation, and then domestic hot water requirement load will be mass of the water that you require multiplied by the specific heat into mains temperature TW minus Tm, the temperature at which water is desired minus the temperature of the mains, the supply temperature. Let us also clarify this TW has nothing to do with the T minimum of 20 C. 20 C and above is acceptable to us, and TW is the set point temperature, and if you compare with a conventional geyser, you may set the thermostat at 60 or 50 or 40. So, this TW is something like this, which is used to estimate only the load, not to be confused that the solar energy system is going to supply at TW. So, the amount of energy saved will depend upon how much of mass of the water is delivered by the solar energy system and at what average temperature or instantaneous temperature one can estimate and compare it to the total amount of domestic hot water load, that will be the fraction met by the solar energy system. So, the relations once again F for the air systems is given over here, first one, and there are corrections for x if the flow rate is different from the standard flow rate of 10 liters per second per meter square of the collector area, and then you have got a correction for the storage, actual storage capacity by the standard storage raised to the power minus 0.30, and the standard storage in this case is 0.25 meter cube per meter square of collector area. Pebbles. A pebble bed storage is usually used for air systems. So, similar relation is given for the liquid based systems. These numbers 1.04, 1.029, they slightly differ, and you have got Xc upon X. If the storage capacity is different from the standard storage capacity, you correct X, and this relation is valid between 0.5 to 4 of the ratio of actual storage capacity to the standard storage capacity. And then the liquid based F chart correlation has been developed for epsilon L C minimum by UAH is equal to 2, epsilon C minimum by UAH equal to 2. So, if the heat exchanger is larger or smaller, the performance will be slightly different, and again the F chart variable X is corrected depending upon the actual size or effectiveness of the heat exchanger. Then F chart has been made useful for service heating, that is, you would like to estimate the solar load fraction if the system is going to supply at some TW, if the mains temperature is Tm and the ambient temperature is Ta bar. So, that is simply done using the air collector correlation or the water collector correlation, liquid based system, as Xc by X is equal to 11.6 plus 1.8 TW plus 3.86 Tm minus 2.32 Ta bar upon 100 minus Ta bar. So, you change the x coordinate depending upon TW and you have a service water heating system, where Tm is the mains temperature and Ta bar is the ambient temperature, the monthly average daily ambient temperature. Once again, I have emphasized this 100 has absolutely nothing to do with the boiling point of water. This is only a scaling factor in defining x. So, TW the minimum acceptable hot water temperature. Now, in order that you calculate the solar load fraction F for a system supplying energy at or above a specified temperature, that temperature being T minimum. So, now the you might say that you want 500 liters per day at T minimum 60 degrees C. So, this may be so many load in joules, or this may be 400 liters per day at T minimum, or maybe 67 L day in joules, same as above. Lower capacity, higher temperature. So, I didn't, because there will be a mains temperature involving, I did not directly proportionate it. This is some sort of a qualitative approximate and qualitative. Not that I have calculated the 67 number, but we know that 67, rather this T minimum should be higher than this, since the capacity is less for a given load. The contention is load fraction will be F1 and F2. Even though the load required or load on the system is the same, if it is being supplied at 60 degrees centigrade, my solar load fraction will be something, and if it is supplying at a minimum of 67 degrees, the solar load fraction differs. So, we have already introduced the critical level, critical solar radiation level, I see as Fr. This corresponds to useful energy being 0. In other words, the solar radiation falling on the collector surface is just sufficient to meet the losses corresponding to that temperature, this on an instantaneous basis. If Ti is the inlet temperature, then IC will be given by this, including this time factor delta T. So, if I define what I call the monthly average daily utilizability, monthly average daily utilizability, let me write it because it is a tongue twister, monthly average daily utilizability. So, basically phi bar is the ratio of solar radiation available above the critical level upon the total solar radiation falling on the collector surface. So, if IT is the solar radiation for any given hour and IC is the corresponding hourly scale critical radiation, when this is positive, there is some supply of energy, and I sum up all these things. When it is negative, I will treat it as 0, that is the meaning of the superscript plus, meaning if the solar radiation falling on the collector is less than the critical solar radiation level, the pump is shut off and we do not intend to cool the fluid. So, this is a good indicator of how much of solar radiation is available to you to supply the quality of energy that you desired. So, roughly, if I do not bother about losses and other system parameters, if you want to have a ballpark value of the useful energy that the solar energy system is going to supply over the month, will be area of the collectors multiplied by Fr tau alpha bar multiplied by the number of days into the monthly average daily radiation on the tilted surface times monthly average daily utilizability. So, this is the solar radiation available above the critical level multiplied by the number of days and optical efficiency and the heat removal factor of the collector being proportional to the area of the collector. So, we define Y the same as we have defined for the case of F chart, Fr tau alpha bar Ht bar n AC by L, and then X is slightly modified and called X dashed Fr UL times 100. Instead of 100 minus Ta bar, we got rid of the Ta bar and just put it in terms of 100, again just a scaling factor multiplied by AC, so that x dashed and y will be comparable orders of magnitude. A correlation will be generally a good correlation if you have more or less all the variables of comparable orders of magnitude, instead of something one of them is 10 to the power 6 and the other is minus 10 to the power minus 3. The effect of that variable in the scale of 10 to the power minus 3 shall not be recognized in general any of the calculations by the load L. So, you have got, after number of simulations, Klein and others have correlated the monthly solar load fraction to phi bar max y. I will tell you why it is called max, minus 0.015 exponential 3.85 f. This I am rewriting to just say that it is a 1 minus exp minus 0.15 x dashed times Rs to the power 0.76, where Rs is the ratio of standard storage to the actual storage. So, the correlation contains the effect of the storage. Now, phi bar is a meteorologic statistic which combines with the operating condition. So, given a location and the solar radiation distribution from day to day, if the system is supplying energy at 60 degrees, 50 degrees, 70 degrees, the solar radiation available to you above the critical level will be different. So, phi bar will be different. So, this is a good indicator of combining the meteorological statistic and the operating parameter, the main one being the critical radiation level or the temperature at which you desire the energy delivery. This has been correlated by Klein as exponential A plus B Rn upon R bar, okay, times xc bar plus C xc bar square, where xc bar is the non-dimensional critical level which we have defined. We should go into non-dimensional critical level, and A, B, C are defined in terms of the clearness index, of course, as such xc bar, which I will call it minimum. If I write it in terms of IC minimum compared to T minimum, this is nothing but the critical radiation level I have not written the time factor, note this, by RT at noon time or at noon time KT bar H0 bar. This is the solar radiation on the monthly average day at the noon time, with which I am comparing the critical radiation level. So, this can be more than 1 or less than 1. So, this is because this is an average level, it could be solar radiation will be higher on days with KT greater than KT bar. So, there will be useful energy gain even xc bar is greater than 1. So, that is what you should remember, that you should not think that the noon time solar radiation is reached and hence there will be no more useful energy above that level, but this is based upon the average day of the month. So, the constants A, B, C are correlated in terms of the clearness index, and then the other parameter which you have to see in the phi bar correlation is, where did I write that? Yeah, this Rn by R bar. In general, I can expect phi bar in addition to xc bar etcetera, a function of phi, beta, delta, and even assuming even after gamma equal to 0. First of all, this correlation is valid only for south facing surfaces, and then it should be a function of the latitude, slope and declination in general. These three have been combined into one parameter Rn by R bar, because this is sort of a stretching factor at the noon time compared to the stretching factor over the overall day, which should take into account the latitude, slope, declination combination. Rn again we have expressed a large number of times in the problems and the derivation. This is it is 1 minus Id by I into Rb at the noon time. This is Id by I times 1 plus cos beta by 2 into 1 minus cos beta by 2 into ground reflectivity rho. So, later on a little more general approach has been followed, and a equivalent mean day utilizability has been defined as omega C1 to omega C2, and IT star, the distribution of the solar radiation of the equivalent mean day minus IC integrated between two limits omega C1 and omega C2 upon the omega SR to omega SS IT star d omega. As a matter of fact, it could be minus omega S to plus omega S also, or and assuming that you take care of the beam radiation component. In other words, certain parts IT star will be non-zero or only diffuse radiation. This can be explained, this omega C1 and omega C2, the critical, it need not be necessarily symmetric, gamma can be 0 or gamma need not be equal to 0, minus omega S plus omega S, this is IC. So, this will be omega C1, omega C2. So, by choosing to integrate between omega C1 and omega C2, we do not worry about IT star minus IC is always greater than or equal to 0 in omega C1 less than omega C2. Okay? So, it can be separated and one can integrate. In fact, it can be done, it has been done. So, this is obtained by IT star omega C1 equal to IT star at omega C1 equal to IT star omega C2 equal to my critical radiation level. So, that equivalent mean day I have not yet defined. What it means is, if this is the Lu and Jordan curve and this is the cumulative frequency kT, and this may be approximately 1, this may be kT bar is equal to 0.67, this is some kT minimum. So, this is on the day with kT equal to kT min, IT noon equal to IC. So, these days QU equal to 0 and these days QU is greater than or equal to 0. So, I will ignore these days and find out average of the clearness indices from here to here. This is my kT bar star. So, IT star hourly radiation on a day with kT bar star. We have in detail explained about how to find out this kT minimum by equating the noontime radiation to the IC. You will find out unknown kT, that will be the kT minimum. So, the logic is the monthly average useful energy sort of multiplied by kT bar into number of days into H0 bar into R bar. Let us look at it what this is. H0 bar into kT bar is H bar, the monthly average daily radiation on a horizontal surface, multiplied by R bar on the tilted surface, multiplied by N is the total radiation, multiplied by phi bar is the solar radiation above the critical level based upon all the number of days in the month. That should be equal to, no matter, though I calculate an EMD, then I shall use the number of days NC. Once again, if this is my curve, this is N1, N number of days in the month, NC equal to N minus N1. This is KT min. So, this is cumulative frequency F, this is capital KT for a KT bar equal to something, right. So, this 0 to 1 can be transformed into N is equal to 1 to 30 or 31. So, I know for simplicity I am writing it in terms of the number of days rather than the cumulative fraction. So, phi EMD into NC into KT bar star times H0 bar star into R bar star. What it means is the solar radiation available to you above the critical level based on the monthly average daily utility and the total radiation for the month over all the days n should be the same as the solar radiation available to you above the critical level on the days of KT beyond KT minimum, above KT minimum, because for KT less than KT minimum there is no contribution to solar energy. That negative contribution is not taken into account in calculating the utilizability. So, that should be the single day EMD utilizability multiplied with the corresponding numbers. From this you can easily calculate phi bar if phi EMD is known. So, which we already have got, phi bar should be simply NC KT bar star R bar star by N KT bar R bar into phi EMD. So, you make a single day calculation, you will get the monthly average daily utilizability, and this is easy to calculate for a concentrating collector or gamma not equal to 0, except when the RB factor is complicated and not integrable, otherwise it can be done. And for modes 2 and 3 you can of concentrating collectors tract, or you can have a numerical integration procedure to get the phi EMD. Originally in the phi bar F chart method, we did not include the tank losses or the heat exchanger. Phi bar F chart correlation does not include tank losses or heat exchanger. So, that is valid assuming tank losses to be 0 or an infinitely large heat exchanger. So, we have devised iterative schemes to take into account the tank losses and the heat exchanger. The basic philosophy being to account for tank losses are accounted for considering tank loss as a load. So, first you guess a tank temperature and calculate the tank losses, consider it to be a part of the load, estimate the phi bar F chart and set up an iterative using the phi bar F chart, find out F and set up a iterative scheme to check whether the guess temperature is correct or not. Similarly, heat exchanger effect is to enhance T minimum to some T minimum plus delta T. Because there is a certain loss across the heat exchanger, the collector has to supply essentially energy at a higher temperature. Consequently, it is a penalty on the performance of the collector. So, you calculate utilizability etc., assuming T minimum plus delta T as a minimum temperature required. In so doing, you will arrive again with a guessed solar load fraction corresponding to this delta T, and you set up whether the amount of energy transferred across this delta T by the heat exchanger is equal to the energy as estimated from the solar load fraction and multiplied by the load on the system. That will set up the objective function to iterate delta T. Of course, both can be simultaneously taken into account. So, then data sources of course, I have given. Of course, at the end of the summary I have given a large number of HTTP or web addresses with which you can go through and get a lot of method. Then we considered energy viability, that is during the lifetime of the in general any alternate energy system, you should be able to save that much of energy that has been used in making those system and its components. Next is the economic viability. There are several indicators like payback period. Now, you calculate whether if the investment is something like 10,000 rupees and you are going to save 2,000 rupees, then payback period may be per year, payback period may be 5 years. Of course, it can be analysis can be complicated by taking into account the inflation of the fuel rate, inflation of depreciation of the equipment and bank interest etc., etc. Nevertheless, payback period is something which is indicative, and that should be, if it is less than the life cycle or the lifetime of the energy system or any other system, then it is viable, otherwise it is not. Normally 2 to 3 years of payback period is acceptable to the industry. Finally, to account for complex scenario, we have considered what is called the life cycle savings method. In short, this is the money saved during lifetime of the system. And if you try to put down all the income mainly due to the saving of the energy and tax benefits and government incentives, that will come as income, and the expenditure could be the repayment of the investment plus the inflation plus the interest rate on the bank and some maintenance plus auxiliary power, all these things come under expenses. So, that is converted into today's monetary value, which is called the present worth factor in the economic terminology, and you estimate over a period of 10 years or 15 years or 20 years, assuming the life cycle or lifetime of the solar energy system. So, the minimum condition is the life cycle savings should be positive. If it is negative, you will not, you can't accept that system. So, that is what it is represented over here. If you have got F versus area curve, which we have drawn a number of times, versus same area versus the life cycle savings, positive, negative. This is as mathematical way of saying if area approaches 0 for very, very small areas, the energy delivered is almost 0, consequently the saving is 0, but the other expenses will remain because you have got the system components. In other words, somebody forgot to put the collectors, so there is a negative life cycle savings. It becomes 0, then it starts increasing, becomes positive and reaches a maximum, then it starts decreasing because you need larger and larger areas for smaller and smaller increments in f. Okay? So, this is the point which will be my area optimum and the corresponding f optimum. So, we choose the area where the energy delivered is maximum per rupee of investment. So, this has been actually modeled by Brandmühl and Beckman, the so called P1, P2 method, which are the economic indicators. One represents the collector loss and the other fuel cost and the system cost. So, I have given a typical figures of payback period, simple calculation only. If you assume the fuel to be coal at rupees 3 rupees a kg, savings per year is so much. This corresponds to the system we have discussed, 12 kilowatt hours, 12 kilowatts for 12 hours a day, which corresponds to approximately 16 gigajoules per month. So, if I use coal at a certain efficiency of 80% or 70%, the yearly saving is so much and the payback period is 21 years, and if it is at 6 rupees a kg, it comes down of course to 10.5 years, and at rupees 10 per kg, it is 6.3 years. And I tried my best. Apparently, the retail coal is not sold, at least at the place I am staying, and I couldn't get real values. And the coal prices at the pit head are around 2000 to 2500 rupees per ton. So, if you assume a certain transportation charge per kg, 3 rupees to 10 rupees seems to be a reasonable number. So, LPG at the old rate of 35 rupees a kg, it comes to saving of 1,26,000. The payback period is attractive, 3.17 years. And if you use electricity at 3 rupees per kilowatt hour, which is on the lower side, it comes to 3.8 years. If it is at 6 kilowatt hour, something like 200 units and above, this comes to only 1.9 years. So, if you compare the solar water heating system supplying or employing flat plate collectors, roughly I think I have taken Rs 8000 per meter square. So, Ministry of Non-Conventional Energy Sources, they have set up a higher limit of per square meter installed cost, including the accessories, 8,000 to 10,000, and larger systems will become little less. And so, if you take a average value of 8,000, this is the payback periods which I had calculated. Then we considered passive systems, and we also recognized there is no strict demarcation of passive devices and the active devices, but nevertheless the following, like solar cookers, and solar stills. This is desalination, produces distilled water. Greenhouse, this can be used in conjunction with a house to keep the house warmer or plants surviving in severe winter, or can be used even as a drying mechanism for something like coffee, tea. Solar ponds, this is basically the concept of combining a collector and a solar device. And then a Trombe valve, it is basically a valve with an air gap through which air circulates, and during the daytime it picks up the heat and it warms the room inside, and natural circulation loop is set up. A direct gain window, if you have colder locations, a south facing window in the northern hemisphere allows the sunlight in winter and does not allow if there is a shade overhang or the shade that much in summer. So, this can be used for passive heating of the rooms. Then in this context I mentioned the shading. So, that is obtained by overhangs or wing walls. This is typically, if this is a window, I may have an overhang like this, and it will shade certain part of the window. There will be a lit part, that means where the solar radiation falls, and this is total area is AW, the window. So, we define shading factor concept, that is what is the total, this is Fi at any instant is A lit, how much of the area of the window is receives the solar radiation, let us say, by the total area. If A lit is 0, Fi is equal to 0, shading factor is 0 if there is no lit area. If it is completely shadowed, Fi will be 0 and Fi will be equal to 1 if it receives fully. So, average or daily value again has been calculated like we do for the tilt factor for direct radiation, IB, RB, Fi d omega upon IB, RB d omega, omega SR to omega SS. It is exactly the, if I say phi is equal to 1, it becomes your IB RB in defining RB bar, and except I remove RB also in the denominator. So, since RB is there, I have put omega SR to omega SS, whereas in the definition of RB bar, you may recall the denominator is from sunrise to sunset. And this can be more easily calculated under extraterrestrial conditions like we have done for RB bar. And as we argued, why RB bar extraterrestrial is reasonably close, RB bar under terrestrial conditions, if simply KT is uniform. In fact, it is identical if KT is uniform, and approximately reasonably satisfies even if it is not. And we have the arguments that significant amount of solar radiation is during a certain time period like 10 to 2 or 9 to 3, and the rest of it is only 10% or 15% of the total daily radiation. And during this brighter period, the clearness index is likely to be uniform, and hence we get the classical result to be quite close even if you calculate with the data or assumed diffuse fraction and distributions. So, we could find a simpler method of calculating Fi or Fi bar if you have got an infinitely long overhang, which will cast the shadow always rectangular. If the overhang is infinitely long. So, this may be achieved something like typically 2 to 3 times the width of the window. So, when once that is the case, this is only a question of estimating this width, which depends upon the time of the day, and we can calculate that with the help of the sun's rays. AS is y into W, where y is the shadow depth or height, which is again given by this relation y is equal to p projection by cos theta z by, where gamma s is the sun's azimuthal angle, which is again related to cos theta. So, the total solar radiation on the window is per unit area of the window is IT multiplied by AW, should be equal to IBRB A lit into ID into AW and rho I into AW. Then finally, IT there contains A lit by AW, giving you Fi, and if I write it on the daily basis, you have got a Fi bar. So, this is how you can estimate per unit area of the window the solar radiation as received, even though it is shaded with different shapes during different times. So, this is a old picture that we have recalled to show you the sun's azimuthal angle, projection of the sun's ray on the horizontal plane, this is the projection. The deviation from the north south line is the gamma s, the sun's azimuthal angle. Okay. This is the gamma s. So, Fi instantaneous can be with simple geometry using the previous relation for y is nothing but Fi is equal to 1 minus tan psi by Rb, where psi is the angle between a plane that is joining the edge of the overhang to the base of the window. So, the simple optics law is that whatever is the solar radiation entering through the aperture will reach the sun. So, I will forget about the window and the overhang system, simply this is psi and this is 90 degrees, beta is 90 degrees plus psi. So, this is a tilted surface facing whatever is the azimuthal angle of the window is with a beta equal to 90 plus psi. So, just you have to evaluate Rb bar for that. Correspondingly, you can write down your Fi bar infinity in terms of tan psi by Rb, etc. So, if you want to calculate a monthly average daily radiation or the Fi bar without calculating going through the Fi bar, you just calculate the daily radiation or the monthly average daily radiation on the plane which joins the edge of the overhang to the base of the window. But this is under the assumption that the overhang is infinitely long. So, essentially you can rewrite your A star, B star and C star in terms of beta star, where beta star is beta plus psi. And okay, these are the standard ABCs for your cos theta expression, A plus B cos omega plus C sin omega, which we have used a large number of times. So, this is the tilt factor for the shading plane, that is what we call. So, the essentially this cosine psi, that angle is nothing but the shading plane window area cos psi by A SHP. A SHP is the shading plane area. So, this is popularly called the shading plane concept. It is simple optic principle, whatever process that, just like the pressure drag. So, that is what I have shown here. So, this is the shading plane ASHP. So, you can basically So, we shall continue in a short time.